Hello, everybody. I hope you're doing well. My name is Karthik Subramanian, and in this video, we're going to go over some probability fundamentals. So, regardless of your background, hopefully this video and the series will give you a good foundation on probability and statistics for use in whatever area interests you. So, let's just dive into it. So, first and foremost, we need to understand what is probability. And probability, simply put, is a way to quantify uncertainty, right? So we have events that are uncertain to occur, right? Sometimes in the real world, we have events that are not very deterministic. So, for example, what's the likelihood of you missing the bus today, right? What if we had a way of quantifying like how likely it was that you were going to miss the bus today on your way to work? So, probability gives us the tools to be able to do that. So, let's start off with fundamentals. So, simply put, the probability in which an event can occur is the number of ways in which the event can occur divided by the total number of possibilities. So, say for example, you have a coin and it's a fair coin, right? So you're gonna have heads on one side and you're gonna have tails on the other side. So when I flip this coin one time, right, we have two outcomes. You can get a head or a tails on one toss of the coin. So the probability of getting a head, right, is going to be 1 over 2. There's one way of getting a heads on one toss, and there are two possible outcomes. So the probability of getting a heads is 1/2, and likewise, the probability of getting a tails is also 1/2. So that's just kind of the simple definition of probability. I guess we can do kind of a quick example, like to make sure we're on board with this and we're all on the same page. So let's suppose we have a bag of marbles, right? And the bag is going to have 3 greens. We're going to have 16 blues. And we're going to have 7 reds, right? So what I want to know is basically, what I want to know is the following. So I'd like to know basically what is the probability of getting a green, the probability of getting a blue, and the probability of getting a red on one draw from this bag, right? So when we're getting a green marble, right, the probability of getting a green marble is 3 greens out of the total number, which is, in this case, 3 plus 16 plus 7, which should be 26. So 3 out of 26 is the probability of getting a green, 16 out of 26 is the probability of getting a blue, and 7 out of 26 is the probability of getting a red. One thing to note about probability is there are a couple fundamental rules, right? So So here's some fundamentals of probability. 1, all probabilities sum to 1. Number 2, a probability is between 0 and 1. So that's what the second condition is saying. And the third condition has something to do with the probability of an event plus the probability of an event not occurring, right? So we call this a complement equals 1. So in the case of drawing marbles from a bag, the probability of getting a green marble is 3 out of 26. But the probability of not drawing a green marble is essentially 23 out of 26. And we can see that there are 23 marbles that are not green and 3 marbles that are green. So we see that the probability of getting green plus the probability of not getting a green is 1. So this symbol here, A raised to the C, that's called complement notation. So it means like the event not happening, basically. So a complement means event A not occurring. So that's just some basic fundamentals of probability, and we're going to need to keep this in mind when we're working out example problems. Okay, so enough with the bag drawing of marbles. Let's make this a little more interesting, right? So what if I wanted to find this? Let's take our marble example. What if I wanted to take the probability of getting green or a blue? So in this case, we have to consider like the chance of getting a green or the chance of getting a blue, right? So we essentially add the probabilities of getting a green or a blue. So that'll be 3 over 26 plus 16 out of 26, which is 19 over 26. Now, this definition does not always work in general, right? So here's an example, right? So let's suppose that we have a 52 deck card, right? So I'm sure most of you have grown up with playing cards. So if you haven't really played cards in a while, here's the composition of a 52 deck card. We have 4 suits, which are clubs, spades, diamonds, and hearts. Each suit has 13 cards. The possible card values are 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. So you see that there are 13 cards in there are 13 different card values, and each of these card values has four versions of it. So for example, like in the case of a 3, there's going to be the 3 of clubs, the 3 of spades, the 3 of diamonds, the 3 of hearts. Likewise for, let's say, a queen, an ace, and so on, right? So what if I wanted to find the probability of getting clubs, right? So the probability of getting a clubs is 13 out of 52 because we have 13 clubs in the whole deck, right? But what if we want to find the probability of getting clubs or kings, right? So you might be tempted to say that it's just the probability of clubs plus the probability of kings, but you're also forgetting the chance that, we can have a card that is both a club and a king, aka the king of clubs. So there's one such card. So we're going to have to subtract the chance of getting the probability of king of clubs. So that's going. So the probability of getting clubs is 13 out of 52. The chance of getting a king is 4 out of 52 because there are 4 king cards in the deck, and the probability of getting a king of clubs is 1 out of 52 because there's only one such card in the deck. So actually, the probability of getting clubs or kings is 16 out of 52. So what do we notice in this example, right? In the marble example, on one draw of marbles from the bag, getting a green or blue cannot happen at the same time, right? Hence, the probability of green or blue is the probability of green plus the probability of blue. But in the case of a 52 deck card, right, if we want to draw one card from the deck and we want to find the probability or the chance of getting clubs or kings, right, well, you do need to account for the fact that the probability of clubs is something, the probability of kings is another thing, but then you also have to account for the fact that you can get a king and clubs at the same time. So the event of getting a club and the event of getting king could happen at the same time, aka there could be overlap. And we don't want to double count the overlap, which is why we have to subtract the probability of getting both a king and the clubs in this example. So this lends us to a concept called mutually exclusive, right? So I'm going to insert this down here. Let me make the font a little bit bigger. Now that's a little too big. So we have mutually exclusive as a concept, right? So we have the following, right? If we want to find the probability of A or B, where A and B are events, it's simply the probability of A plus the probability of B minus the probability of A and B. So if you want to get a good visual of what I'm talking about, imagine we have a Venn diagram, right? So we're going to have a Venn diagram as such, and this circle here is going to represent event A, and this circle here is going to represent event B, and this box is going to represent stuff outside. We don't have to worry about that. We'll get to that a little bit later. So what I'm going to notice is the probability of A or B happening is pretty much like the area of this region here in green, right? But what are you going to notice? We're going to notice here that the probability of A is going to be all the stuff I shade here in red, right? And the probability of B happening is going to be all the stuff here I shaded in yellow, right? But what do you notice? The red and yellow overlap in the middle, right? And this middle part here is probability of A and B happening. So when we're adding the red and yellow regions, that's adding probability of A plus the probability of B. But you also are adding the overlap twice. So we have to subtract out the overlap. So that's why this is the formula to find the probability of A or B happening, right? And what makes two events mutually exclusive is if they cannot happen at the same time. So in our case of the marble example, when we're drawing a green or a blue on one single draw, you cannot get a green and a blue in that one moment of a draw, right? It's impossible, right? So the probability of getting both a green and a blue on one draw is 0. So there would be no overlap between drawing a green versus drawing a blue. So we don't have to really subtract out overlap. So this case, this example here is what we call mutually exclusive. So if we want to take the probability of events A or B occurring, and you know that A and B are mutually exclusive, the probability of A or B is simply probability of A plus the probability of B. And we don't really have any overlap. So events A and B are mutually exclusive if the probability of A or B equals the probability of A plus the probability of B. So that's important to understand about mutually exclusive events, right? Another thing I will show quickly with this Venn diagram example, let me draw another one down here, is the idea of the complement. So suppose now we have event A. So basically, event A is this circle right here, right? A complement, or not A, will be pretty much all this region outside of the circle representing A. So this region is what we call A complement. So this is not A. So just something quick I wanted to show. It's kind of what really helps in these probability problems is drawing out Venn diagrams for your events and identifying the overlaps and identifying which areas to really consider, right? So just something important to consider. So yeah, that's just a quick side note of what a complement is. So that takes care of mutually exclusive. I guess kind of a quick example is this. So here's a quick example. Suppose we have that probability of A is 0.8 and the probability of B is 0.4. What is the hold on uh, yeah, I'm just typing out these numbers, so give me a moment. So suppose we have that the probability of A is 0.8, and we know that the probability of A or B is going to be 0.2. No, that would no, that's a bad example. Let's say it's 0.6, and we have that the probability of A or B happening is 0.8. So what we want to find is this. Let's find the probability of B. Are A and B mutually exclusive? So this is just kind of a quick example to make sure we understand what this is. So what we're going to do is just simply apply our formula. So we know that P of A equals 0.6, and we know that P of A or B equals 0.8. So we know that P of A or B by definition is P of A plus P of B minus P of A and B, right? And I'm going to add another given here, I forgot. So the probability of A and B happening is 0.1. So let's see if we can use that to find P of B, right? So I'm going to change these numbers a little bit. So we know that the probability of A is 0.6, the probability of A or B is 0.8, and we know that the probability of A and B equals 0.3. So we want to find probability of B. So we know that 0.8 equals 0.6 plus P of B minus 0.3. So when we solve this, we see that P of B equals 0.5, right? So we know that the probability of B is 0.5. To check if A and B are mutually exclusive, we just have to see can A and B happen at the same time. Since A and B can happen at the same time, right? Namely, P of A and B equals 0.3. Events A and B are not mutually exclusive. So that's just something important to note. So we're going to keep that in mind. So hopefully that is a quick exercise to make sure you understand mutually exclusive. All right. The next concept we're going to talk about is independence, right? And you actually have seen, and now that you think about it, in your daily life, you actually have kind of witnessed independent events. So let me jot the section. So here's like a colloquial definition of independence, right? So two events, A and B, are independent if the outcome of A doesn't affect the outcome of B, right? Now, let's think of a simple example, right? So suppose we go back to our coin toss example. We have a fair coin where you can get heads or tails, but we're also going to spin a spinner, right? And the spinner is going to be divided into three sectors. So you're going to have a 1, 2, 3, and you're going to spin it around. And the areas of these like regions are equal on the spinner, right? So if I flip a coin, right, and I get heads or tails, logically, that wouldn't really affect, what I get on the spinner, right? It's not like the coins and the spinners are really like talking to each other in secret and that, getting a heads on a coin toss will affect what I get on the spinner. It just doesn't really work that way, right? If you think logically, right? So in this case, tossing a two-sided coin versus spinning a spinner, those events are independent. So now we can compute probabilities in a much easier way, right? So if we want to find the probability of A and B, and we know that A and B are independent events, we can just simply say that the probability of A and B is the probability of A multiplied by the probability of B, right? So I guess as a quick example, what if we wanted to calculate the probability of getting a heads and spinning a 2, right? Well, since we've established that getting a heads or flipping a coin and spinning a spinner are events that don't affect each other based on the outcome, we view them as independent. So this is just simply equal to P of getting a heads times the probability of spinning a 2, right? So the probability of getting a heads is going to be 1/2, right? Because we're assuming a fair coin. And the probability of spinning a 2 is 1/3 because we assume that the spinner has equal sections. And thus the probability is 1/6. So when we know that two events are independent, it sometimes makes the probability calculations much easier because we can split a joint event such as A and B happening together into the product of the individual probabilities. So that's just something cool to keep in mind though. Another prominent example of independent events is rolling two six-sided dice. So if you have like a die basically and you are, rolling the two dice, you could view those as independent, right? Because the outcome I get on one die shouldn't affect what I'm going to get on the second die, right? And we're going to assume for the sake of simplicity that the die is completely fair. So assuming this six-sided die representation, right? What is the probability of getting, what's the probability of getting a 1 on the first roll and getting an odd number on the second roll? Well, we said rolling the two die were independent, so the probability of getting a 1 on the first roll is simply 1/6, whereas the probability of getting an odd number on the second roll is simply a half, right? Because the possible numbers you can roll on a six-sided die are 1, 3, and 5. Those are the odd numbers. 2, 4, and 6 are the even numbers. So it's just going to be 1/12 probability. So that's just a quick example. Um, and one more nice example that I would probably like to go over is this. So here's a brief exercise to see if you're understanding this. So suppose we have the following, right? We have that the probability of A or B occurring, right, is 0.5. We know that the probability of A is going to be 0.6. And we have that the probability of B is going to be 0.5. So basically what we want to do is find the probability of A and B happening, right? And we can see are A and B independent events. So let's check this. So we want to find the probability of A and B, right? So that's what we don't know. We know that the probability of A or B from earlier is the probability of A plus the probability of B minus the probability of A and B, right? So we know the probability of A or B is 0.5. We know the probability of A is 0.6. The probability of B is 0.5. And the probability of A and B is what we're trying to solve. So we see that 0.5 equals 1.1 minus probability of A and B. We find that the probability of A and B from doing this algebra is 0.6, right? However, what is probability of A times the probability of B? Well, that's going to be 0.6 times 0.5, which is 0.3. Which is not equal to 0.6. Thus, A and B are not independent events by our definition of what it means to be independent. So hopefully that gives you a straightforward overview of what independent events are. The next topic I want to move on and discuss a little bit more in detail is conditional probability. Um, it's actually kind of used a lot, especially if you're into data science and machine learning. You'll see conditional probabilities a lot of the time. So let's make a section for that. All right. So what is conditional probability? So if you haven't heard the word, conditional probability is a way of saying, given that an event happened, what is the probability that something else happens? So I guess an example in the real world could be something like this, right? Suppose that you didn't study for your exam, right? Given this fact, right? What is the probability of getting an A? Now, you should always make sure you prepare for your exam and get a good night's sleep. But for the sake of example, we want to be able to use probability theory to find this, right? So to encode conditional probability, we simply say probability to encode this scenario, right? We can say probability of getting an A given didn't study, right? So this bar means given in English, right? So when I read this notation, what this is saying is what is the probability or likelihood of getting an A on the test given that I didn't study, right? So that's what this notation means. And we're going to be talking about this like quite a bit though. So yeah, I guess one way to do this is to draw a table. This is kind of a good way to learn this. So let's actually simulate this scenario though real quick. So let's say we have a class, right? And we kind of poll students on getting an A, right? Versus not an A, right? And we also have a situation of study and not study, right? And we're going to pull the class, and here are the numbers we get, right? So for students who have gotten an A from studying, we see that 95 of the students did that, right? For students who studied but didn't get an A, I would say 15 of those students was the case. Now, for students who got an A without studying, that's probably going to be 5 of them because maybe the course might be a little difficult. For students who didn't study and didn't get an A, probably 80 of these students fall into that category. So from this table, what do we want to find? Well, let's start with something easy. What is the probability that the students studied for the exam, right? What is the probability of getting an A? Let's find these two things real quick, right? So to find the probability that somebody studies, right, we have to figure out how many students in total have studied for the test versus over the total number of students. So we're going to get some totals here. So we see, let me move this a little bit so we can have some room to calculate our total. So for students who studied, right, that total would be 95 plus 15, right? So students who studied and got an A plus students who studied and didn't get an A, right? So we have 110 such students, right? For students who did not study and get an A, and students who did not study and didn't get an A, we have 85 such students who didn't study overall, right? So we're kind of ignoring like what grade they got and just focusing on how many students have studied versus how many students didn't study, right? So that's what these totals are representing. Now, let's do the same thing, but figure out how many students have gotten an A and how many students did not get an A, right? So we see here, 95 plus 5, so 100 students have gotten an A, right? We don't care, in this case, of whether the students studied or not. We cared about how many students get an A, right? And likewise, for the number of students overall who did not get an A, 95 such students, right, didn't get an A. So when we take the total, right, we see that there's 195 students total in our data set, right, based on my sample, right? So to find the probability that a student did study for the exam, that will be 110 out of 195. We just simply look at the totals, right? 110 students studied out of 195 students. And likewise, the probability of getting an A would be 100 out of 195, right? Now here's where conditional probability gets a little interesting. What if I asked you this? Let's simulate our scenario above, right? What is the probability of getting an A given didn't study, right? So in this case, we know for a fact that you didn't study for the test. We just want to see given that, what is the probability of getting an A, right? So we have to shift our mindset a little bit, right? We know that we didn't study for the test, right? So how many such students didn't study for the test? As you can see in the table, we see 85 students have not studied for the exam, right? So 85 becomes our denominator, right? Because we are conditioning on a known fact that we did not study for the test, right? So we care about the total number of people who did not study for the test. So that's 85. Now, among these 85 students who didn't study for the test, how many of them got an A? Well, we see 5 out of the 85 have gotten an A among students who didn't study. So we can say this: the probability of getting an A, given that you didn't study, is 5 out of 85. As a quick exercise, let's try this. Let's try the other way. Let's try the probability of that you studied, right? Given that you got an A. So I'll give you a moment to attempt this on your own, and let's see and compare to see if we got the right answers, right? All right. I'm sure like you kind of have an idea or kind of just want or you have given up, but in this case, let's talk about it, right? So again, we're conditioning on the fact that we got an A, right? So how many students in total have gotten an A? Well, 100 such students have gotten an A. Now, among those 100 students who got an A, how many of them studied? Well, that's 95 of those students, right? So the probability of studying for the exam, given that you got an A, is 95 out of 100. So it looks like here, right, we have a really good chance of getting an A if we study for the exam. So I guess the life lesson here is make sure you guys study for your tests and don't procrastinate till the last minute because you want probability on your side. So that's kind of a brief review about what conditional probability is. Let's go into a little bit of definitions. So what do we notice here, right? Um, we notice something really, really neat, right? We know that the probability of studying given gotten A is 95 out of 100. But when we did our analysis, we kind of were thinking about this, right? We were taking the ratio of studying and getting an A divided by the probability of getting an A, right? Let me move this over a little bit. So another way of approaching this conditional probability problem is to think in terms of this, right? Among students who have gotten an A, right? What is the chance that they have studied? So the probability of studying and getting an A is 95 out of 195, right? Because we're dividing by the total number of students, right? And the probability of getting an A, right, in general, right, is 100 out of 195, right? So let's do a little bit of math here, right? Let's simplify this fraction a little bit. So that's going to be 95 over 195 times 195 over 100. That gives us 95 over 100. So it looks like here we found another way to compute the conditional probability. So let's generalize a little bit. So the probability of event X occurring given that event Y happened is simply the probability of X and Y, right, divided by the probability of Y occurring, right? So this gives us another cool formula to find conditional probability, right? And why are we talking about conditional probability right now? This will make a lot more sense when we get into something called Bayes' theorem, but I just want you to have this in the back of your mind, right? So that takes care of conditional probability. Let's see what else we got here. Okay, and one more thing. Let's take a step back and come back to this marble example, right? There's another interesting thing we can do with marbles, right? So let's use the same marble example, right? So we scroll above. We have 3 greens, 16 blues, and 7 reds. Now I'm gonna kind of do something a little interesting here, right? I want to pose this question, right? Suppose we draw 2 marbles from the bag, right? What is the chance when we draw marbles, we don't replace? What is the probability of getting a blue first, then a red? So let's figure out what this question is asking. So we have this bag of marbles, and when we draw marbles, we don't replace. So if I take a marble out of the bag, I don't put it back in. That's called without replacement, right? And basically, we want to find the probability of getting a blue first, then a red. So we want to find probability of blue equals first draw, right? And red on the second draw, right? So what we can do here is this, right? We know that like when we draw a marble from the bag, our second draw probability is actually affected by what we draw. So we can't necessarily view these two events as independent because drawing a marble from the bag on the first draw affects the probability of drawing another color on the second draw, right? But if we look back at our definition of conditional probability, right? Another handy trick is that the probability of x and y is equal to the probability of x given y times the probability of y. So what did I do here? All I did was I just multiplied this p of y over to the other side. So that's why I'm getting this relationship here, right? So we can do something similar, right? So we draw a blue first, and given that I've drawn a blue, what's the chance of getting a red? So this probability is simply equal to probability of red given blue times the probability of blue, right? And I'm kind of using the conditional probability a little bit loosely though, but you'll kind of see what I mean, right? So when we have drawn a blue marble, the probability of that happening is 16 out of 26, right? But now, after drawing the blue marble, how many marbles do we have left? Well, we have 25 marbles because one marble has been drawn. Now, among those 25 marbles, what is the probability of getting a red on the second draw? Well, you still have 7 red marbles to choose from, right? So 7 out of 25 is your probability of getting the red marble on the second draw. So this is going to be your probability of getting a blue first and then red. What if we wanted to do this? Probability of 2 blues in a row. Well, we can just kind of do similar reasoning. So the probability of getting a blue on the first time is 16 out of 26. But when we draw a blue, right, we don't replace, right? So we have 25 marbles left to choose from. But how many blues are remaining? We have 15 such blue marbles, right? So this is your probability of getting 2 blues in a row, right? So that's important, right? Now, what if I change the scenario a little bit? So suppose we now can replace marbles after a draw, right? Find the probability of drawing a blue first, then a red, right? So in this case, when we draw blue first, it's 16 out of 26, right? But we're going to put the blue marble back in when we draw. So there's still 26 marbles remaining, and 7 out of 26 is the probability of taking a red. So we multiply the two events together, right? Since both need to happen, right? So this is the probability of drawing a blue first, then a red on replacement. So that's kind of what this example is getting at. Hopefully this example gives you a quick teaser into basic probability fundamentals, what is mutually exclusive, what is conditional probability, what is independence. So hopefully this example kind of, or this video kind of gives you a brief refresher on this topic. And I hope to see you in the next video. Thanks for tuning in.